So we're happy to have Gleb Terentiuk from Michigan, who will give us a background talk on etale, fundamental group, and local systems.
Thanks for introducing, and it's nice to speak here. So, I'm going to talk about etale, fundamental group, and local systems. And there's practically much proof, so please feel free to interrupt me and ask any questions if anything is not clear. Okay, so the goal for the first part of the talk is for connected scheme X with a choice of geometric point. So K bar here is an algebraically closed field, and I have a map from the spectrum of this field to X. We want to define a profinite group which is going to be denoted by one etale X bar. So there is a scheme and a geometric point as inputs for this group. And this group should be, well, something related to the fundamental group we know from topology. However, the way you define a topology, you use loops and some homotopy equivalences, and it's not clear what is the right analogy in algebraic geometry. But fortunately for us, there is another way to define fundamental group. Namely, there is a nice observation that, so let's say X here, it's a reasonable topological space. So reasonable means that, for example, path connected and locally simply connected is enough, but for example, any finite C doubly complex works. So if you have such topological space, there is an equivalence between two categories. One category is covering spaces over X. Another category is the category of sets with an action of the fundamental group. So any point on X defines you this equivalence. So it is the category of by one sets. And this is good news for us because, so this is kind of the thing we want to understand, the fundamental group, without, well, want to understand it without using loops. And this category is equivalent to covering spaces, which we can make sense of in algebraic geometry. And moreover, from this category, it's possible to reconstruct by one. So therefore, since these categories are equivalent, it will be possible to reconstruct by one from this category. And the way you reconstruct it, so it's a purely, well, it's just an abstract fact. So if you have a category, if you have a group G, discrete group G, and you consider the category of sets with an action of this group G, so you can forget the action. It gives you a functor from this category to this category, and you can compute the automorphism group of this functor. Well, definitely definitely G maps to this group, because what does it mean to give an automorphism of this functor? It means for any element in the image, you should provide an automorphism in a compatible way, but G knows how to act on sets where you forget the action of G. So it maps to the automorphism group, and it's an automorphism. So it gives you a way to reconstruct G from this functor. In particular, it gives you a way to reconstruct pi 1 from this category. You just forget about action of pi 1 and use the automorphism group of this functor. So therefore, the upshot is that it's possible to reconstruct pi 1 from this category, covering spaces. But maybe another fact which is kind of similar, but we'll need it, is you can do this similar computation where you consider only finite sets. So if you consider G, or finite G sets, and you forget the action, then it's also possible to compute the automorphism group of this functor. And it turns out you can write down the formula. The formula is going to be, so it's going to be a limit where you take finite quotients, so n here runs through normal finite index subgroups, and they form an inverse system. If you have two normal subgroups, one inside of another, then there is a map from the quotient by the smaller to the quotient by the bigger. So you can take the inverse limit. And so it's also denoted like G hat. It's called profinite completion of G. Right, and it's not that surprising. This is also not hard to see because, so here you have finite G sets which look like G mod n, and it's more or less enough to know what happens for these sets. So you only kind of see the finite quotients of your group G. Okay, and now let's try to do this.
Sorry, quick question.
Yep.
It's not the annoying question. Do we need to take like tensor preserving models, or is for some reason we don't need to take it?
Tensor preserving tomorrow. So you have some tensor structure in mind. I don't think we need. I think it's just two plane categories and automorphism as a functor between two categories, unless I'm mistaken. But I think that's. Right. Okay. And now, so again, the upshot is that we can recover pi1 from this category. So let's try to find an analog of this category in algebraic geometry. So in the analog of this category, it's finite etale X schemes. So now I have connected scheme X. So elements here are maps from Y to X, which are finite etale. It's a reasonable analog of, well, finite covering spaces. And so this category is denoted like this, right? And now we want to define pi1. So it means we need to take automorphism of some functor, and this functor under this equivalence corresponds to forgetting the action. And when you trace what happens here, you basically take the fiber over the base point. You have a covering space, you have your base point, you take a take the fiber, and there is an action of pi1. This is how this equivalence works. So, if I have a geometric point mapped from spectrum of an algebraically closed field to my scheme X, it produces a functor to just finite sets. And this functor takes this object to the fiber over, so you have a map from spec K bar to X, and you can take the fiber product. It gives you a scheme over K bar, but it's a finite etale scheme over K bar, and it's basically a collection of points. It's the joint union of spec K bar. And right, so this is my functor f x bar, and now we can define the fundamental group. So fundamental group X with respect to x bar is defined as the automorphism group of this functor that we constructed. So I take this functor and I take its automorphism group, and yeah, this group, it carries a natural topology somehow because the target is the category of finite sets. It carries profinite topology. And yeah, let me probably say some remarks before doing examples. Well, first of all, if you have, for example, 2 points, 2 base points, then, well, as in topology, the fundamental groups are isomorphic if the topological space is connected, and here it's the analogous story. So there is an isomorphism between these groups, but it's to construct this isomorphism, you just construct an isomorphism between two functors, but you have to make some choices, and at the end this isomorphism is well defined only up to inner conjugation, but the same thing kind of happens to topology, so it's not that surprising. And right, and maybe we can also kind of analogous thing to what happens in topology. Now this category of finite etale schemes, it's under this, well, this functor identifies with the category of finite phi1 sets, where by this I mean so finite sets with an action of this group, but with a continuous action. It means that it factors through the finite quotient of this group, but it's right, it's automatic. And right. And the last thing I want to say is that, well, this group is functorial. So you have, if you have a map from x to y, and you have a base point in x, so you can compose it to get a base point here. It gives you a map from pi1 of x to pi1 of y. So it's a functor if you choose base points in a compatible way. And now let's maybe do some examples. But are there any questions so far?
The thing you have off of is that like f, so k bar. It's kind of hard to see.
Sorry, where?
The very end of the line in the middle of the board.
Here.
It's like where you wrote ought.
Definition.
Yeah, is it ought of f k bar of the functor?
So it's of x with respect to the geometric point x bar. So I need to fix the geometric point, and then I reduce this group. Because the functor depends on the point. You take the fiber, so you need to have x bar as a data.
Okay, the thing inside the ought is fx bar?
Fx. Fx bar. Part of the, yeah, Fx bar.
Sorry. Yeah, it's fx bar, yeah.
Okay,
It is functor.
Yeah, it was just kind of hard to read.
Yeah, sorry.
This time.
By the way. Any other questions? Okay. Yeah, well, there is a natural question whether this group is related to the fundamental group from topology we know about. So let's try to understand it. So let's say I have a scheme over complex numbers. Let's say it's finite type. Right, then given such data you can take its C points. Let me denote it XAN. And well, this set carries a topology coming from topology on C. And if you started from a variety, it's going to be a complex variety. And well, now let's say you have a finite etale map from y to x. So it's an element from this category, and well, you can apply this functor to this picture, and you get a map from a multiplication of y to a multiplication of x. And it turns out that this map, it's a finite covering space. And moreover, it turns out that this functor, it's an equivalence. So any finite covering between these two things, it comes from some algebraic map. So it defines an equivalence between the category of finite etale schemes over X to the category of finite covering spaces over multiplication of X.
Does X have to be smoothed over here, or we don't assume anything about it?
Yeah, I think it's not needed. But yeah, I think you can reduce to the, yeah, I'm not sure, but I think it's not needed. I don't know the argument. Okay, right, and this functor, it gives you a map. So remember that pi1 etale is defined as a homomorphism group of kind of functor from here to finite sets. But this functor gives you a map from topological pi1. Well, you can choose also base points compatibly. It will give me from topological pi1 to etale pi1. Just because you see that the category of finite etale schemes, it's a full subcategory in the category of all covering spaces. So if you have endomorphism of the category of all covering spaces, you can restrict it to finite covering spaces. So it gives a map like this, and it becomes an isomorphism after profinite completion of the topological fundamental group. So, in particular, this abstract group that we constructed, it had this comparison with the usual fundamental group, but it knows only its profinite completion. Yeah, this is automatic once you know this is an ellipse, which is, well, this is harder. Okay. Yeah, let's do an example. Outside of complex numbers, so if your X is just a point, so it's a spectrum of a field K, then you can ask what is the pi1, and pi1, well, first of all, again, we need to choose the geometric base point, but it amounts to choosing an algebraic closure of K. So, and yeah, this is more or less by definition is the Galois group of K bar, which is basically choosing X bar over K. And yeah, this is also a topological group with the profinite topology, and it's a continuous isomorphic. So, in particular, you see that this pi1, even for a point, it's something interesting unless the point is algebraically closed. Okay, and let's do another example. So, if I have a field F, let's say it's finitely generated over Q, then I can look at the GM over F bar, and I can try to compute this by one. Let me omit the base point, well, since for computation doesn't really matter. So the answer is going to be, so it's going to be a profinite completion of Z hat, but well, GM is defined over Z. When you put back to F bar, there is an action of the Galois group of F on this thing. So there is an action of the Galois group of F on this group, and we will also try to understand this action. And well, to compute pi one, if we want just to use the definition, we need to understand the category of finite etale coverings over GM. So let's say we have a finite etale covering. Let's say Y is connected and the degree is n, so it's n to 1. What we can do, we can compactify everything. GM has a unique smooth compactification, which is by 1. And I can also compactify Y. Well, and now this is some projective curve over F bar, and we can use the Riemann-Hurwitz to compute its genus. So this curve, well, it's finite etale over GM, it means that we allow ramification on the 0 at infinity. Let's say that over 0 we have y1, ys, they go to 0. And let's say over infinity we have y1 prime, yr prime. And well, each of this point has some ramification index, so denoted by d1, ds, and d1, dr. So we know that the ramification indices should sum up to the degree. So and now let's apply the Riemann-Hurwitz. So it says that I can compute the genus of this curve. Well, the genus of P1 is 0, so it's -2 times the degree. And here I have contributions coming from the ramification. But, well, we can rewrite this, right? Because sum of EI is n, but we have to subtract the number of the points, so it's going to be n minus r plus n minus s, so n's are going to cancel out, and what you're left with is just this number. And now, well, this number is non-positive, right? So it means that this number is also non-positive, but it happens even only if they all say at least 1, so this is at most -2. So it means that the genus should be 0, right? So it means that genus is 0. So it means that this curve must be pi1 because we're over an algebraically closed field, so it has a point, therefore it's rational. And now, well, if we think what it means, so we have a map from P1 to P1, sorry, which is ramified over 0 and infinity. So it means that this map looks like z to the power n times some constant, but since again the field is algebraically closed, you can make change of coordinates, and you can erase lambda basically. So it means that kind of up to isomorphism, the only connected finite covering of degree n is just given by raising to the nth power from gm to gm. And now we need to understand the automorphism group of this covering. Well, and it's kind of easy to see that. So we need to understand all automorphisms of y over gm, and by the formula we see that we can only multiply z by nth root of unity. That's the only possibility. So it means that automorphisms of y over gm, well, canonically, it's the set of nth roots of unity in f bar. And well, it gives you the answer that the etale fundamental group. So it means for any n you have to choose nth root of unity in a compatible way. So this gives the answer. And well, non-canonically it's z hat. But from this presentation you can see the action of the Gleb group. Let me denote this as G sub F. Because any automorphism of F bar, of course, it permutes roots of unity. So it gives it the action. And you can also denote it. Okay, that's an example of, well, an easy example of computation of pi1. Are there any questions about this example? Okay, let's move forward. Okay, this is kind of the first part about the fundamental group. Now let's discuss the second part of the name of the talk. So, local systems. And yeah, let me define local system. So definition is motivated from the picture we have in topology, that you have the monodromy representation, and you can think about local systems as representations of pi1. So let me denote UL local system. So QL local system NX is a continuous homomorphism from pi1 of x to GLM QL. And again, so this group has profinite topology, and this group also has topology. Namely, you have topology in DL, you have maximal compact group here, GLM DL. And topology here is basically you just define fundamental neighborhoods of the unit, and these are defined as I'll use R here. Right, and I want this homomorphism to be continuous. So this is a definition, and the main source of, or one of the big sources, I guess, is kind of the same thing as in topology. If you have a smooth proper family, you can take the cohomology of the fibers, and it will give you the representation. So if you have X to S, which is smooth and proper, you can think about some, if like S is a curve, you have a family, so you have a base point, and you have the fiber as this base point, and if you have a loop, the fibers vary, and it gives you, it gives you an entomorphism of the cohomology of the fiber, and this is the monodromy representation. So right, so it gives map from pi1 tau S with the base point to automorphisms of the homology of the fiber. So this is etale homology, which you can think about as analog of singular homology. And right. So this is the representation that we have from this picture. And you can ask, like, if you have a random representation of pi1, whether it comes from such a family or not. Yep.
Do we want some condition like L is invertible?
Oh, yeah, thank you. That's actually important. Yeah, I want L to be invertible on the base. Yeah, thank you. Right, because it uses the smooth base change, and for the smooth base change, you want L to be invertible. Right. Okay. Yeah, and it turns out that representations coming from this way, they actually have some extra properties. Namely, so if you have a loop and you see you see what is the corresponding operator, it has to be quasi-unipotent. It's a theorem of l-adic. So let's try to understand why. Okay, let me start with the following theorem. So let's say we have, again, F finitely generated field over Q. And let's say,
When we say a loop, presumably you mean some special loops.
Yeah, I think, right. I want it to be like a generator over the puncture. If I have different punctures and I multiply, I think it's gonna break down. But yeah, thank you. So it's some local. Okay. Okay. Right. So now I have finitely generated field over Q, and I have a representation of the Galois group of this. So this is a notation for the absolute Galois group of this field. So I have representation. I have a QL local system, and then the claim. So in particular, it's a continuous homomorphism. Then the claim is that if you restrict, well, here you can take, well, there is an extension of this field where you take f bar and you take Laurent series with coefficients in f bar, so it gives you a map backwards. And this group is isomorphic to z hat. And the way I think about this is like, you think about Taylor series as kind of a disk, and Laurent series, it's a puncture disk, and pi 1 of the puncture disk is z. So this is kind of the analog of this fact. And the claim is that, okay, let me denote the, well, in particular, there's a map from z to z hat. So let me denote the image of the map by sigma. So this action is quasi-equivalent. Well, it means that if you take some power of the matrix corresponding to this generator, then it's unipotent, which means that this operator is nilpotent. Okay, yeah, that's, I'll try to explain the proof of this theorem. So if you have any questions about the statement, then please ask. Yeah?
This is like the case when this representation comes from the gel.
No, it's any QL local system over, yeah, you have kind of spectrum of this field, and you have any QL local system. Yep.
I guess it appeared earlier too, but where does the finite generation come into?
Sorry, what?
Finite generation of
Right. Yeah, I think for the computation of GM, I'm not sure, but I think it doesn't matter for computation of GM. But here it matters because kind of the, well, the main thing you want is that F doesn't contain all the L power roots of units. And if it's finitely generated, it's the case. But if it's, right, this is kind of, you will see this in the proof. Yep.
G sub Laurent series and T over F, that's just the Galois group of that.
Right, yeah, sorry. The notation is that like G of a field K, it's the absolute Galois group of this field. Yep.
So this computation that Z had is equal to Galois, is it true for any like?
Any algebraic closed field. It kind of, it uses that if you have a finite extension of this field, it's basically given by extracting nth root of the T.
characteristic of zero.
Right, yeah, characteristic. Right, otherwise, like when you extract these roots, it's not that great. Yeah, some of it. Any other questions?
What's the generator sigma there?
Sorry, what is the generator here?
Yes.
So it's just, well, this thing has a natural map from Z, and I take the one, kind of one in Z, and I look at the image, kind of.
Yeah, I mean, like, how does that naturally describe on the gamma F bar?
I think it's kind of the, well, if you think about extensions of this thing as extracting roots of T, I think it's kind of cyclotomic. So it's, yeah, well, it's kind of, it multiplies in a compatible way by roots of units.
So you probably have to make a choice of
system of versatility to define the generator, but your statement is independent of the trace.
Right, yeah. Thank you.
So
Yeah.
you're saying that it naturally corresponds to the Z hat twist by one.
Well, yeah, I'm not sure.
That Z hat is more easy.
Okay. Yeah, I guess. Right, yeah, once you fix kind of roots of unity, it gives you this. But yeah, as Sasha pointed out, the statement is true. You don't need to choose it. Just okay, yeah, let's try to prove this. Let's see if I can move. Okay. So, the first step in the proof is that, well, we have here local system, and I want to prove something about the image of this element. But first, since rho is continuous, well, here we have this subgroup where we take neighborhood of unit. And it's pretty much open. This is open, and well, open subgroups here, they correspond to a finite extension of your field. So you can find a finite extension K such that when you restrict your representation to this normal open subgroup, it actually lies in here, so it's vector to this 1 plus L squared matrix. Right, so in particular, for any element here, its image is some matrix which is congruent to 1 modulo L squared. And so here we have this group that we want to understand. Well, and it lies, it goes to the, it sits in the maximal and implied extension of K. And so the Gleb group of the maximal and implied extension of K, it's also non-canonically Z hat, and it maps to the group we're interested in, because this is an extension of this field. And we want to prove something, we want to prove something about this map that is quasi-unipotent. So, but here you have the generator, let me call it tau. So it goes to like n sigma. And if you prove that tau is unipotent, it implies that sigma is quasi-unipotent, because its power, its nth power, is unipotent, right? So it's enough to understand this map from this group to here. It's enough to prove that the generator here acts as a unipotent operator. And, well, to understand it, first observation that this group, it's pro-L group, and therefore, since this homomorphism is continuous, you actually only care about the L part in the Gleb group of Laurent series. So let me denote KL to be the L part of K bar. So it means that I take so we take the maximal unamplified extension of K, and we add all L power roots of the uniformizer, right? So this is this field has evaluation, t-adic evaluation, and you can extend it to the finite extension of your field. So you have an uniformizer, and kind of explicitly, this field is given by you add all L power roots to the maximal unamplified extension, And the key fact is that when you restrict your representation to the Gleb group of k bar over this maximal L part, it goes to 1. Because, well, this group, even though it's infinite, but in some sense it has order prime to L, well, in a sense that it's a profinite group, so it's a limit, it's inverse limit of finite groups, and each of these finite groups, it has order prime to L. Somehow, because all the L power extensions, they sit here. Explicitly, it amounts to showing that if you have a finite extension of this field, all elements there are L power of other elements. So, and there are no maps from groups, so, well, but since it's continuous kind of, it factors and you get a map from a group of order prime to L group, and it's necessarily trivial. So therefore, rho, so this representation, it factors, so it's a map from here to here, and it factors to the quotient by this subgroup. And the quotient is just given by the Gleb group of this L part over K. And now we have to understand this map. And, well, we can use the structure of this group. So again, this group, this field, you construct it, you start from an ramified extension, you add some roots. So you can do this in 2 steps. So here you have this open, this normal subgroup, K bar, sorry, KL over maximum ramified extension. And the quotient is the Gleb group of the ramified extension over K. That is the same as the Gleb group of the residue field. Let me denote it like this. Well, moreover, again, if you remember this field, it's defined, you just extend some roots of the uniformizer. So you can identify this group with the l-adic Tate module. Because for each finite extension, again, you can act only by multiplication by L power roots of unity. So this is right, and this group that we're trying to understand, it's an extension of something we more or less understand, and the Gleb group of the residue field, and we need to understand how this group acts here, right? But this isomorphism, it's compatible with the action of this Gleb group on the Tate model. There's natural action, right? Because any antimorphism again permutes roots of unity. So, and well, let's denote the character giving this action by chi. So non-canonically, this is ZL, and we have this character. Right, and now, so we need to understand what happens and what matrices we get from elements in this group, right? Because this is the thing we're trying to understand. Okay, so if I take any element here, well, this group acts by conjugation here, but using this compatibility with the cyclotomic character, we see that these 2 elements are conjugate for any element T in the log group of the residue field. And now the magic is, so let's take the logarithm. So we have the matrix corresponding to this element acting in our representation, and we can take its logarithm. It makes sense because, well, logarithm, it has expressions like 1 minus thing to the power over something. But if you remember, all the elements are congruent to 1 modulo L squared. So when you subtract 1 and takes power, it's going to be highly divisible by L, and it makes the logarithm, well, it makes sense to take the logarithm. And we see that these two things are conjugate, let me know by x. Well, by the formal properties of the logarithm, this is the same as this. Okay, so these two matrices are conjugate. And, well, it imposes some conditions on the characteristic polynomial of this matrix. So let me denote AIX to be the ith coefficient of the characteristic polynomial. So it's like elementary polynomial in the eigenvalues. And, well, since these matrices are conjugate, they have the same characteristic polynomials. But also, if you just look at this matrix and you compute it, well, you see that it's equal to this. And now, well, this is a pretty strong condition. If this number is not 1, it implies that this thing is 0, right? So now we just need to find t such that this is not 1. Yeah, and here we use this condition that f is finitely generated. So it means that there is no finite extension which contains all the L power roots. It means we can find an automorphism T such that this thing is not ith root of unity, so it's not 1. And it implies that coefficient is 0, so it means all the coefficients, well, if I at least 1, are 0, so it means that x is nilpotent. But now, if you remember, so we cared about the generator of this group, and we understood something about the logarithm of the operator corresponding to this element. But now we can recover the original operator, so this is nilpotent. I can take exponent of this, it makes sense. And this is just exponent of the logarithm, so the thing we started from. And, well, if I take exponent of something nilpotent, what I get is something unipotent. Right, and that ends the proof because we see that the generator of this group, it goes to something which is unipotent, and yeah, we win. But are there any questions about the proof? Yep.
Can you just recap what happened on this board on the right?
On the right.
Yeah.
Right. So, yeah, I have an element in this group, and it acts in my representation. There is a matrix associated to it, it's rho of s, and I want to prove that it's unipotent. And yeah, the trick is that, so if you take logarithm of this matrix, then you observe that for any element in the Galois group of the residue field, these two matrices are conjugate. Because, well, this group, it acts here by conjugation, and by compatibility with the action of the l-adic Tate module, you see that it implies that these two matrices conjugate. But this is a very strong condition. And it implies that all the coefficients are 0 because two matrices are conjugate, so the coefficients are the same. And now you just need to find t such that this is not 1 for any positive I, but it's not a very big deal. And for example, if you know that no finite extension of your field contains all L power roots of unity, then it implies that you can find t such that this is not 1, and it implies that all the coefficients are 0. So it means matrix is nilpotent and its exponent is unipotent. So yeah, it's
What is this notation? Like you have 2ix or something?
sorry, AI, it's thank you. It's I coefficient of characteristic polynomial of X. So it's ith elementary symmetric polynomial in eigenvalues. Yeah, the proof somehow is, it's a bit of magic for me, but I think it's real nice. Yeah.
What's x of t? Is it like one of the maps in the short exact sequence?
X of t. Sorry, it's chi. It's this cyclotomic character,
Oh, it's
which gives the action of this group on the. Sorry, yeah. I realized that it had the same letters. Sorry.
That's it.
Yep.
Can I just try to say what's happening on this board?
Yeah, sure,
Slightly
please.
different way. So if let's just assume chi of t is an integer, so you have a matrix which is conjugate to its power, just some power. So if you have an eigenvalue, let's say the nth power of that eigenvalue is also an eigenvalue. Right? So now lambda is an eigenvalue, lambda at the n is an eigenvalue, lambda at the n squared, and so on and so forth. There's only finitely many eigenvalues, so that means lambda is a community. So we showed all the eigenvalues for this which is the same as being quasi.
Yeah, thank you. Okay, and now let's try to get a corollary from this result, which I think due to Terentiuk. So the corollary, so the result is just some statement about Galois groups of all-around polynomial, well, field of all-around polynomials, and the corollary is actually about geometry. So let's say I have a map from X to S. Yeah, S is going to be a curve, well, a projective curve with one puncture. So this is over BC. I want it to be smooth projective. And also I want, let's say, this is a projective curve. Right. Then the statement is, so, well, when we have such a situation, smooth projective morphism, it gives us this monodromy representation on the homology of the fibers, and the claim, so let me choose some random thing. It's going to be S prime, it's going to be S, another point. So I have this representation on fibers. Yeah, and the claim is, well, this puncture, it gives me a map from, I have a map from this spectrum of Laurent series to this curve, this punctured curve. And, well, on pi 1, it gives you a map from, well, the lab group of this field. Right, and the claim and this is quasi, so geometrically you have a family with one puncture, and you have a family, sorry, you have a curve with one puncture, you have a family over this curve, and you look at the loop around this puncture, and the operator it induces on homology of the fibers, it has to be quasi-equivalent. And this is, yeah, what I was trying to say here, that kind of these representations coming from geometry, they have this special property, that kind of eigenvalues are roots of unity. It's a very, pretty strong condition. Again, the beautiful thing is this theorem it follows more or less immediately from this abstract theorem, namely that this is a smooth projective family, and you can think like if X is given by some finite amount of equations in the affine space, since there are only finite amount of equations, there are only finitely many coefficients involved, and therefore all this picture you can find finitely generated field over Q, and if you just have to take all the coefficients which are involved to define these schemes. And you can find a family. Okay, this is I don't S, but math cal. So you can find a family over F such that you spread out this family and the fiber over the geometric point recovers your original family, right? Well, once you spread out the family, it gives. Okay, so we have this representation. On the fibers, and it extends to representation of the Gleb group. Well, now we have a map from Lorentz series over this field, because you also have a puncture on this curve. Well, and it extends in the sense that once you restrict it to here, you recover the original representation. But now we're in the situation of this theorem, right? We have the representation of this guy, and once you restrict it to this subgroup, you get a quasi-idempotent operator, and yeah, it says that this is quasi-idempotent. And basically, yeah, we basically finished the proof, which is really nice because you observe some geometric statement just from playing with Gleb groups. Okay, yeah, I think that's all I wanted to say, so thank you.
Yeah, when you are looking at a geometric point of your scheme, and you can you take the etale I1, which is that geometric point, does the group that you get only depend on the scheme theoretic point underlying the geometric point?
I think so. Yeah. Because if you have another one, you can just construct an isomorphism between fiber functors, and it will give you an isomorphism between fibers.
The data of scheme theoretic point is more data than the data of geometric point, right? Geometric point is a Coulomb's cost transfer.
A very basic question. Can you say how to get this map, like from Pi1 etale to G, each of the fiber?
From this?
Yeah, like the monodromy.
It's not basic. it uses a lot of stuff. It uses, well, you need proper base change, and you need smooth base change. But yeah, basically it amounts to showing that if you have x to y, and it's smooth and proper, then you want to prove that these are z mod l to the power n local systems.
So say I assume this, and then can you get sorry, I feel like I'm just blanking.
Yeah, well, now you want to prove that if you have L mod n to the power local system is the same as giving Z mod, yeah, it's the same as giving a representation of pi1, and these, right, how does it work? Yeah, just one, I want to say that there is an equivalence of categories.
So those sheaves are actually represented by a finite etale x.
Ah, yeah, thank you, yeah. Right, this is, I think, how it is.
It's just an object in this like cycle.
Right, it's, yeah. And then if you pass to the limit, and it gives you this ZL in QL.
And here for the map from the Gala group to Taiwan, that's just choosing some point in S. The state
this one.
Yeah.
Right. Like you have this puncture, and when you delete a point, well, I want to say if you delete a point, it gives you a map from the spectrum of this thing, which you think about like punctured disk to your scheme, and then you just take one of this stuff.
Is there any reason why we want S to be a curve? Like is this S bar?
Well, one reason is that this is a statement we can prove. I mean, like if you have not a curve, then you have to modify the statement, because now you want to delete not a point, but like a divisor. Because if you have something high dimensional, you delete a point, it doesn't change by one. And then you should care about how good this divisor is. And I
think the statement you made is literally true when the S is higher dimensional.
Yeah. But yeah, you can try to make a meaningful statement for a higher dimensional base, but then you should care about how good your divisor is. I know nothing about this.
You just said like if you remove just one point, the pi one does not change. So like the pi one of S bar and pi one of S are the same.
I mean, if like S is not a curve, but imagine a topology you have some threefold, and you do the point, then any loop can just doesn't matter.
So it's kind of like removing this point is sort of like making this pi one of S meaningful.
Yeah, like if you have like a sphere, there's no pi one.
Right.
When you do the point, you have this loop around.
Sure. Yeah.
But I mean, I think that if you just ignore the fact that there's an S bar and stuff, it's a contentful statement, right? It says that like for any map from C double parentheses T into your scheme, the sort of element of Galois always goes with something plus you can put into representations of geometry. That's true. The proof is works.
Right.
But how much this Gala group captured the pi one of S? Like if S bar was really like a sphere, then like is this map from Gala group to pi one of S? Like how close to isomorphism?
If it's just a sphere without point, it's an isomorphism.
Isn't it?
If you have like n punctures, you have n loops. But like, yeah, if you take all n loops, there is one identity, as we learned from Daniel's talk. But I mean, like abstractly, it's a free group in the non-topological sense. In the topological sense, sorry. Yeah.
Let's say if you have like a non-compact, right, S, and then like you have this like GC double bracket includes this pi one. Is it like always realizable as like some like monodromy operator on like some compact?
Sorry, you have non-compact thing, like a curve here is non-compact. Yeah, you take this operator, and what if you want to be the realizable?
Can you always realize that like you compactify S, like this like the sense boundary, and then like the monodromy operator on the infinity? You can always do this.
Yeah.
Well, this infinity might already accidentally be inside your horizon. Yeah, it gives you a valuation of the field fractions. I mean, the spec C double, it's even more so maps to S bar, for instance.
Any last question? All right, let's try it again. And maybe we'll plan to start at 5 past.